Hello, and welcome back to my YouTube channel. My name is Professor Govalla, and today I'm going to be talking to you about what an inductor is. And specifically, we're going to be diving into this equation right here to the right. And just like all my other videos, I like to first start off by defining an inductor. And this definition says that an inductor is a passive element designed to store energy in its magnetic field. An inductor is considered to be any conductor, which can be copper, aluminum, or silver, of electrical current that inherently poses inductive property due to the magnetic field generated by the flow of current. And we say that to enhance this effect, this magnetic effect, in practice, we rotate a coil of wire, as shown in white here, over a cylindrical core, or simply just a core. And this core can be made up of, this core right here can be either air, iron, or ferrite, which is a certain type of ceramic material. So to begin this lecture, really, we want to define or to understand what an inductor is. We want to, define things like magnetic flux and magnetic flux linkage. And again, this is a symbol for inductor. So this is our end goal, L. So I'm going to come down here, and I'm going to say then that we want to define, or very, very important, what is magnetic flux? Okay, what is magnetic flux? So imagine if you have a loop of wire, just one loop. Okay, this wire is going to have what we call a cross section area, and I'm going to denote this as S. We're going to say the number of turns it has is 1 turn. And if we apply a current through this coil of wire, okay, current have this properties where they generate what's called magnetic flux density. So using the right-hand rule, or actually, let's consider my current going the other way so that the right-hand rule is consistent. So let's go in this direction. Okay. And this can also be done using a permanent magnet. What's called the magnetic flux density denoted by B is generated. And essentially, this is how concentrated the magnetic field lines are in a given area. All right, so that's what it means by magnetic flux density. So given this configuration, and depending on the current, again, depending on this current that goes through it, or a permanent magnet next to this loop, we generate what we call magnetic flux. So magnetic flux is equals to the magnetic flux density times S, again, which is the cross-sectional area. And this is in terms of Weber, okay? Or again, this is denoted as WB. This is named after a German scientist named Wilhelm Weber. Yeah. So now we have now we know what magnetic flux is, right? So this is magnetic flux. This here is magnetic flux. Let me just call this MF density. Okay. And this is the cross-sectional area, CSA. Okay. So the next thing we want to study is the what's called the magnetic flux linkage. So I'm using a different color here. I'm going to call this the magnetic flux linkage. All right. Now imagine you have not just one loop, but you have another loop, and then you have another loop, and then you have another loop. Okay. So the number of turns up here was one turn, but up here we have 4 turns. And let's just call this N. And if we apply a current through it, so we said if we apply a current, so this current's coming in here, and it's, if you can imagine, it's rotating across this entire wire, something like this, all the way to the end. It's going to generate a linkage. So let me use red. So it's going to generate here. Okay. Something like this. Something like that. All right. And then we consider that we define that the magnetic flux linkage of a coil, which is denoted by lambda, denoted by lambda, is equals to the number of turns N times the magnetic flux. All right. And this is what we consider Weber turns. That's the units. All right. So now let's go ahead and break lambda down. Okay, let's expand on lambda. And we could say then that the magnetic flux linkage, lambda, all right. So again, remember, the magnetic flux linkage is just simply the magnetic flux. So if you understand what this is, how we get this, or the intuitiveness behind magnetic flux, when you multiply it by the number of turns, you get the magnetic flux linkage. That's all it is. So then this equates to the number of turns times, I'm going to replace the magnetic flux density B times the cross-sectional area of my, in this case, this is my core. In this case, it's just air, times S. So then let's go ahead and define the magnetic flux density. And this can be defined as N times, let me use a different color, this mu H, all right, times, again, cross-sectional area. This H, what this H is telling us is the magnetic field intensity. And as it says in the name, it's basically the intensity around this turns of wires given a current. So we could say that H is the number of turns divided by L times my current that I apply in there. All right. So let's put in what we know for H first, and then we could say that then the magnetic flux linkage lambda is equals to the number of turns times this mu times N over L, or let me write mu actually with a different color since we haven't defined it yet. N over L times I times S, and this is equals to mu N squared times S over L. All right, and then we multiply this by I. So there's a lot of physics going on here, but I'm hoping that we're trying to understand where everything is coming from. Just to recap, or I guess I'll recap at the end. But again, if you need to rewatch the first part of this video, please go ahead and rewind it and really, really understand it. But let's go ahead and describe this mu term. And this mu term is what we refer to as the magnetic permeability. If you haven't checked out my what is a capacitor video, we do talk about capacitors there, and we talk about permittivity, to permit. But here we talk about permeability. And I'll explain where this word stems from in a little bit. But a magnetic permeability of a specific material. Okay? And this, the units of this are Henry over meters. All right? And we consider that mu is equated to mu r times mu naught, where again, this is the relative permeability of a given material. And this is unitless. And this here is the permeability of a vacuum. Okay. And this is given to us, or let me call this our free space. You could call this our free space. And the number for this is 4 pi times 10 to the negative 7 henries over meters. Again, this is in henries over the named after the scientist. This can also be generated as 1.256 times 10 to the negative 6 henries over meters. All right. So again, the reason why this relative permittivity is unitless is because UR is equals to mu over mu naught. And this is henries over meters over henries over meters, which is just unitless. All right. The word permeability stems from the Latin word to permeare, okay, or stems from the word permeate, okay, permeate. This means to pass through, all right? So basically, and the material we're talking about here, so for example, when we say given material, when we have our core, if this is an iron core, and we apply current through a wire, all right, the magnetic field, how easy is it to generate a magnetic field that passes through this iron core, right? So I hope that makes sense. This permeate, right, meaning passing, to pass through. It's talking about how easy is it for it to pass through this iron core, okay? All right, so at this point, we should know what everything is in our equation, right? So again, our magnetic flux linkage equation, let me start fresh, is lambda is, let me call this mu r mu naught n squared s over L, this is a lowercase l, times I. Okay, so we say then that when we're talking about inductors, this right here, we call this capital L, and it's in the units of henries. So you might wonder yourself, how do we get henries from here? We consider that, again, mu r is unitless, so it doesn't have a unit. Mu naught is Henry over meters. The n is a dimensionless quantity. It's turns squared or loops squared, but it doesn't have a dimension, right? So we disregard it. And the cross-sectional area has a unit of meters squared. And then obviously L has a unit of meters. So then this just becomes henries because these two cancels out with this. So we can consider that our equation for the magnetic flux linkage is L times I. All right, next what I want to do is I want to describe the magnetic flux linkage in terms of currents and voltages, right? So I'll come down here and I'll say, let's describe magnetic flux voltages and currents, okay, or voltage and current. And we need to do that. We need to listen to Faraday's law. And Faraday says, as the magnetic flux linkage in an inductor changes with time, it induces a voltage V across the inductor's terminal. Okay, so doing a bunch of experiments, he realized that as this magnetic flux linkage, so all right, if you can think about it as if you have an inductor and you have at t is equals to a certain time, you have this as your magnetic flux linkage. So this is t, let's say, is equals to 5. And then at t is equals to 10, it changes to be bigger. So this is t is equals to 10. You're going to induce a voltage. There's going to be a change in voltage. All right, across, again, we said that this is, let's say this is A, B. There's going to be a change in V. All right, so I hope this proof or this law makes sense. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. So we can write an equation about this, right? A very simple equation we could say is that Michael Faraday is saying that V is equals to the change in magnetic flux linkage divided by the change in time. But we know that magnetic flux linkage is this D times this, what we call an inductor or inductance, times I over dt. So then if we pull out the L, we get L di over dt is equals to V. So this is where you get that beautiful equation, which all electrical engineers should know. Okay, so I hope this makes sense in terms of how we've integrated it from the lower level all the way to the high level, right? You should now understand this equation and where it comes from. So now, unlike a capacitor, in an inductor, we say that voltage changes instantaneously, but current cannot change instantaneously. So again, let's use this equation to prove that. So we say that if dt is equals to change in t is equals to 0, then di over dt is equals to di over 0, which is infinity. So voltage V is equals to L di over dt is equals to C times infinity is equals to infinity. But again, obviously this V is limited because we can't really get a time is equals to 0, right? So for a very, very small time, a very, very small change in time, voltage changes instantaneously, right? And it's limited by the maximum current that you put in or your capacitor value, things like that. Another example, so let me call this example 1. So another example is consider if dt is equals to 0. So this means there's no, di. Consider di is equals to 0. So that means there's no change in current. So what does this mean? If there's no change in current, we consider this a DC current, right? And V is equals to L di over dt. So this is L times 0 over dt, which is 0. So we say that in DC, an inductor actually acts like a short circuit. And this is, again, the opposite of a capacitor. A capacitor acts like an open circuit in DC, right? So what we're saying here is if you put a DC current, so IDC, let's just say I is equals to, let's just say 4 amps into a coil of wire that's an inductor, it's just going to be, and you connect this to ground, it's just going to be, the current is going to go to ground, right? It's just going to act like a wire. But in this situation up here, if I were to put an alternating current, okay, what's going to happen is when I'm at the first peak, the first half, the first peak, this magnetic field might, let me use the passive, so it's going this way. So it's going to generate a magnetic field this way. And when I'm at the second peak, it's going to generate a magnetic field going the opposite direction, right? Because using the right-hand rule. And depending on the inductor value, we're going to get what we call a change in voltage across this terminal. All right. Okay, so the next thing we want to do is we want to consider writing my current. So we want to represent IL of t, which again is just I of t, which can just be I, in terms of V of t, or again just V. So what I'm going to start is I'm going to start writing my equation. V of t is equals to L di of t over dt. I'm going to write the right-hand side. I'm going to move it over here. So this is going to be di of t over dt is equals to V of t over L. What I'm going to do now is I'm going to multiply both sides by dt. All right. So then this just becomes di of t is equals to V of t times dt over L. Let me go ahead and take an integral on both sides. So this is t from t0 to t, t0 to t. When I do the integration of this, I get I of t minus I of t naught is equals to 1 over L 0 to t, or t naught to t v of t dt. Okay, so then we have I of t is equals to I of t naught plus 1 over L from t naught to t v of t dt. If we take that, so if t naught is equals to 0, so then this means that, let's say t naught is equals to 0, I of t naught is equals to I of 0 is equals to 0. Then we have this equation, I of t is equals to 1 over L from 0 to t v of dt, right? And this is a case where the inductor is uncharged. All right. So as you can see, if we apply a voltage, right? If we apply a voltage through, right? Because time can be 0, right? So if we apply a voltage through here, we're never going to get an instantaneous change, right, of current. The current is always going to be changing as well. It's never going to be instantaneous. All right. I don't want to dive too much into this, but power. So power, simply put, P of t is VI, right? So this is L times I di over dt. So that's your power equation. Where positive power, if you do this and you get a positive power, this means that the inductor is charging up. And if you get a negative power, this means that the inductor is discharging, right? Or delivering power to a circuit. So let me do an example here really quickly to end the video. All right. So consider you have this example and someone says, all right, this is my current that is inputted through an inductor of 0.5 henries. And they want you to draw the voltage output that's going to be generated. So the first thing I'm going to do is I'm going to write an equation for this current. And I'm going to say then that I of t, all right, is equals to, or let me actually bring it down here. I of t is equals to, so rise over run here. Rise is 6, run is 2. So this is minus 3t. The y-intercept is plus 6 from 0 to 2. 0 between 2 t and 4. It's going to be, again, rise over run here, which is 3t. The y-intercept here, right? So it's dropping by 6 every time. So this is 6 or negative 6. And then here will be negative 12. So this is positive 3t minus 12 from 4 to 6. And then it's 6 otherwise. All right. So we want to use our equation. So this is simple. We want to use our equation and simply say V of t is equated to L di over dt. So then the derivative of this times 0.5 is negative 1.5 from 0 to 2. The derivative of 0 is just 0 from 2 to 4. And the derivative of this is just times 0.5 is 1.5 from 4 to 6. And then obviously the derivative of 6 is just 0 otherwise. So in this graph we draw, we're going to see that instantaneous shift. So here we have, this is our V of t. This is t. Let me do my units here. This is t. So here we have minus 1.5, and then it shoots up. It changes rapidly, right? So here, my voltage, you're getting an induced voltage of 1.5, and then since current is not changing, I get 0 voltage through. And then since current changes again, I shoot up and I get a voltage across my terminal of 1.5, an induced voltage. All right. And then it goes back down and it's DC again. So then I get 0 volts as being induced in DC. It's just acting like a wire. All right. So let me say this is 2, 4, and 6. So this is the answer to the question. If you got this, give it a thumbs up in the comment section below. If you have any questions about this, please let me know, and I'll be sure to get back to you. Again, this is a very important concept for all electrical and computer engineers to know. If you like my channel, please give me a sub. Like the video, share the video, and share my channel. Thank you. Have a wonderful day.